So here's some practice that's very similar to some of the examples that we just did. And if you're wondering how these types of problems might show up on an exam, these problems are taken directly off of old exams. So these are old exam problems. So we start with this first one, C9H12O2. We can calculate the degrees of unsaturation, and we should get 4, which, as we've seen many times previously, does suggest to us that we have an aromatic ring present. We can also see the alcohol group that's present here. Now we can scroll down and look at our proton NMR. Again, I'm just going to rewrite our formula so we have that to refer to. And we know that we have 4 degrees of unsaturation, which means that we likely have an aromatic ring. And we know we are very likely to have an alcohol. So the first thing that we see are these 2 doublets in the aromatic region. When we have these 2 doublets, that's almost always a sign that our aromatic ring is going to have 2 groups at opposite ends of the ring. Because that gives us a ring where these 2 carbons are equivalent, these 2 carbons are equivalent, but they're not equivalent to each other, and so they will split each other into 2 doublets. The next thing that I see is a pattern that we've already seen 2 or 3 times, and that's this quartet triplet pattern. And what have we said multiple times that that's most likely to stand for or represent? An ethyl group. And more specifically, because the higher the CH2 peak is at around 4 ppm, tells us we have an OCH2CH3. So I'm going to fill that in on one side of our aromatic ring. So at this point, we've accounted for 8 out of our 9 carbons. We know based on the IR spectrum that the other side is going to have an alcohol group. So at this point, there's only one way to do that, because we have 1 carbon and 1 oxygen to account for. And so that gives us this as our final structure. Is that consistent with our carbon NMR? So we have 2 peaks right next to each other around 60 ppm. That's consistent for carbons that are next to oxygens, and we do have 2 of those. We also have a peak down here around 10 ppm, which is consistent with a carbon at the end of a chain, like that one. Finally, we have 1, 2, 3, 4 aromatic carbons, which is consistent with this type of structure as well. All right, let's go on to number 2. Our formula here is C9H10. So how many degrees of unsaturation? We get a total of 5. So again, fairly likely that we have an aromatic ring. The other thing that the IR is pretty boring, to be honest. We have this big cluster of peaks around 3,000. We know that represents our CH bonds. And everything else is in the fingerprint region. So that's actually pretty important, because that suggests that even though if our aromatic ring accounts for 4 degrees of unsaturation, we still have one more. And so that suggests to me that there's very likely no alkene. So if there's no alkene, how are we going to account for another degree of unsaturation? Well, that means we're going to need another ring in addition to the aromatic ring. So here's our proton NMR. And what I see here is, in addition to a sort of cluster of aromatic peaks, so it's not a nice aromatic region, we have a triplet and a quintet. Well, a quintet is 5 peaks, and that means we know that it's next to 4 other hydrogens. So, for example, it could be next to 2 CH2s. So if we draw it like this, each of these CH2s are currently equivalent, and they're next to 2 hydrogens, which would make them a triplet. The CH2 here in the middle is next to 4 equivalent hydrogens, which makes it 4 plus 1, or a quintet. So how does this connect now to the aromatic ring? Well, we can't just do it like this, or one of them would become a CH3 at the end. So the splitting patterns wouldn't match, we wouldn't have the symmetry of this group, and we wouldn't have the extra ring that we need. But if we took these 3 carbons and connected them in this way, it won't change our splitting patterns from what we proposed here, and it does account for our extra degree of unsaturation. Does it fit our carbon data? Well, for our carbon data, this molecule is completely symmetric. And so we would expect to see 3 aromatic carbons and 2 that are not. 3 aromatic carbons and 2 that aren't. So spectroscopy, as we've said before, is about doing a puzzle. And it's a puzzle where we have to try and figure out, how do we put the pieces that we have, how do we figure out what the pieces are, and once we have them, how do we put them together? So finally, let's do number 4 here, C8H10O. Gives us 4 degrees of unsaturation, and we should recognize the alcohol peak here. So likely at this point that we have an aromatic as well as an alcohol. Now again, we see our triplet and quartet, and so that suggests to me that we have an ethyl group. But we also know here that the ethyl is not going to be attached to the oxygen. So that suggests that the ethyl is directly attached to the aromatic ring. Then we have a singlet here representing our alcohol, and we'll put the alcohol opposite of the ethyl group because of this pattern that we've seen repeatedly, the two doublets. And so there's our structure. So problems like this, I would recommend doing more of these. And I've posted more problems like these on Blackboard. You'll find them in a file labeled Spectroscopy Practice Problems or something similar to that. You'll find at least a half dozen more of these types of problems. And I would encourage you to work through more of these. And then I'll be happy to go over any questions that you might have on these, either during any sort of live session we might hold or in any session where we meet online.